So welcome back to this sequence about how you can construct and observe tuples. Some values are naturally made of several other values. For example, if you want to represent a citizen, it is composed of a name, a first name, and a social security number. If you want to represent a point in 2 dimensions, then you need an abscissa and an ordinate. So how in OCaml can you construct and observe such kind of values? Let us define the origin of the plane as a 2-dimensional point in OCaml. To represent a 2-dimensional point, we want a tuple, and the 2 components of this tuple will be equal to 0. So this is written like that. You first open up a parenthesis, followed by 0, a comma to separate the components of the tuple, and right after that, the second component of the tuple, and you have to close the opened parenthesis. You can notice that the top level inferred the type of this expression to be a tuple of size 2, so a pair, whose first component has type int and the second component has type int. And of course, you can do that for many different values of the integers. So the same example can be written by first introducing a type identifier to represent the type for 2-dimensional points. So we reuse what we have learned in the previous sequence by introducing a point2D identifier. And this point2D identifier can be used to constrain the type of the origin identifier to be assigned the type point2D. Now that we have seen several examples, let us review the general syntax rules. At the level of types, you can compose 2 types to form a tuple types by using the star operator. At the level of the expressions, if you want to construct a tuple, you just have to separate the expressions that construct the different components of this tuple and separate them by commas. So now we know how to construct a tuple, but how can we observe it? Observation of a tuple, or in fact of any structured data in OCaml, is based on pattern matching. Patterns describe how values are observed by the program. And they appear in late bindings and as function arguments. In fact, we already saw the simplest form of pattern, identifiers. When you have an expression of the form let x is equal to 6 multiplied by 3 in x, you can read it as I observe the value of the expression 6 multiplied by 3 by naming it x. There is another form of pattern which is very simple and is used to say that you just want to ignore some components. This is called a wildcard pattern, and it is written using an underscore. So when you have the following expression, you can read it as I ignore the value of 6 multiplied by 3. In order to observe the different components of tuples, you just have to compose the patterns for these components and separate them using commas. For instance, the following expression is read as I observe the first component of this tuple and I name it x. And I also ignore the second component of this tuple. So let us first define a tuple, which is a pair of 2 integers. If I want to name the first component of this pair and to ignore the second component of this pair, I just choose the pattern that starts with an identifier pattern followed by the wildcard pattern. And I see that the top level has only named the first component x, which is equal indeed to 18. Of course, this pattern can be used as arguments of the function, just like that. So it's a general function that always returns the first component of any pair, and the second one will return the second component of any pair. So let us review the general syntax for tuple patterns. In fact, you just have to write a pattern for each component and separate them using commas. The only constraint is the fact that the number of subpatterns must be equal to the number of components of the tuple you are pattern matching. Also, you have to make sure that an identifier is used only once in a pattern. Now in the machine, a tuple is represented as a heap allocated block, which means that you have a block in memory with several cells inside it, and there is one cell per component. So for instance, if you have a tuple P with 1, 2, 3 inside, then you have a block with 3 cells. The first one contains 1, the second one contains 2, and the third one contains 3. Now, if you have an identifier P which represents the value of a tuple, internally it is represented as a pointer to the memory. So if you define, for instance, Q whose first component is P, it means that in memory the first cell of this pair is in fact a pointer to the first block. Now, pointers can be shared, which means that if you change the second component of Q from 0 to P, in fact, you will have 2 pointers in the pair, and the second one points to the same block as the first one. So now let us talk about equalities. In fact, in OCaml, there are 2 kinds of equalities. The first one is the structural one that you have already seen in previous weeks. 2 values are structurally equal if they have the same content. Now the operator double equals implements what is called physical equality. 2 values are physically equal if they are stored at the same place in memory. So it means that the 2 pointers are in fact equal. So let us define 2 pairs x and y, and also an identifier z, which is equal to x. So what do we have here? The first thing to notice is the fact that if you compare the contents of the 2 pairs, they are equal. But now, if you use this physical equality to compare the 2 pairs, x and y, this time they are not equal because we have allocated 2 different blocks in memory. So the addresses of these 2 blocks are different. Now, when we have written that z is equal to x, in fact, we have shared the same pointers in the value assigned to the identifier z than the one that you have for x. So x is physically equal to z. Now, what kind of programming errors can you do when you write patterns? The first one is to use not enough or too much subpatterns with respect to the number of components of the tuples that you are analyzing. As already said, you can't use several times the same identifier in a pattern. This is called a nonlinear pattern. What is nice is the fact that the compiler will code that kind of error for you at compile time. So you will have the guarantee that your execution of the program will not fall into that kind of problems. So if you write a pattern which is expecting two components and you try to observe a tuple with three components, then it is of course invalid. And the compiler is able to warn you because the two types of the pattern and the expressions are incompatible. You cannot name two components with the same name because it doesn't make sense. And again, the compiler is able to detect that kind of errors and produce a type error. There is another kind of programming error that you can do when you use patterns over tuple. And that kind of error cannot be caught by the compiler because it is a more semantic problem. Indeed, definition using an index can be error-prone. So the following definition of abscissa is well-typed, and this definition of ordinate is also well-typed, except that there is an error, a semantic error, because the abscissa should be here x, and the ordinate should be here y. But the compiler is not able to understand that you've made that kind of errors. Fortunately, we will see that another kind of types will help us avoid that kind of semantic problem.